Hello.
Yeah, I was just saying hello. That's it.
Yes, yes. Okay, so hello everyone. Let us start our second meeting. So today I will discuss about vector spaces, what is the meaning of subspace and linear independence span basis, those exercise related to those things. So what is vector space? Vector space is a set V together with two operations. One is addition, another operation is multiplication. So how those two operation works? So additions works in this way: V cross V2 V, that is given two element V comma W, we can add VW. And addition needs to satisfy some properties, that is addition is closed, it is associative. Another thing is that addition, there is an element 0. Okay, there exists 0, and every element V has an inverse minus V, that is inverse. So what is the meaning of associativity? It means that two element, if you add three elements, suppose u, and first add V plus W and then add u, it is same as u add with V and then add W. What is the meaning of 0? There exists an element 0 in the vector space V such that addition with 0 gives the same thing. And what is the meaning of inverse? It is like, for take any V belongs to V, there exists an element minus v belongs to v, such that v and adding minus v, this will gives the zero element. So that is, we can say in a single word that v with the structured addition, this gives an abelian group. Sorry, I have missed one condition, that is v plus w. This should be same as w plus v. That is, addition is commutative. If a space has,
Sir, one question, sir.
yes,
This inverse last time, maybe I'm wrong there, but isn't it like v into v inverse is equal to 1?
no, here I am saying that inverse with respect to addition. That is, you can
Okay.
say minus of v.
Okay. So in with respect to
It is additive
multiplication.
inverse. You can say it is additive inverse.
Okay. Okay.
And
Thank you.
zero is additive identity. Okay. So those are the operation, and v with respect to this operation forms an abelian group. There is exist another operation, multiplication. So multiplication operates in this way. There exists a field. Suppose F be the field on which V is defined. Okay, vector space is a structure which is defined over a field, and we are taking F script this F to be the field. Then we can multiply. That is, given an element from field, we have a map, multiplication map, field cross V to V, and those maps satisfy some structure. That is, if suppose A and B two element from field, if you multiply in this way, and if you multiply after multiplying V, multiplying with B, those two will be the same thing. Similarly, it satisfies distributive property. And the right side also. This is left distributive, and there is another right. So those are the things need to be satisfied. And another thing is, field always has a identity element 1. 1 multiplied with v, this gives v. So if the addition and multiplication, we call it scalar multiplication, satisfies all the properties, we call the structure to be a vector space. That is, V is a vector space with respect to addition, multiplication over the field F. Now we we are familiar with the with many vector spaces. For example, if you consider the field, so what is the meaning of field? Field is abelian group, and there is multiplication structure. That is multiplication. If you know what is abelian group, I have just defined above. So and there is another thing, multiplication. That is, if you consider, if you remove 0 and if you consider f minus 0, then there is another operation, multiplication. So rename it at as dot. This need to be a group also, abelian group. This is also abelian group. We call this structure to be a field, and there is addition and multiplication are compatible. So the same addition and multiplication should satisfy a dot b plus a dot c. So then we call the structure f plus and dot is field. Okay. So this is the definition of field. Some example of field are like real number. This is the most common example. Real number is, because addition with addition, under addition it is a abelian group, and if you take r minus 0, then multiplication is also abelian group, and the compatibility also hold. So r plus dot, this is a field. Another example of field will be like subspace, rational number and addition multiplication. This is also a field. Complex number, addition multiplication. This is a larger field. And another thing you can say ZP. So Z modulo P, or you can write in this notation also Z mod PZ. This is also a field. Okay. So what are the example of vector spaces? Most common example is this example. Take any field, for example, take R, and you take R to the power n. R to the power n means it contains tuple of this form a1, a2 up to an. Okay. For example, two-dimensional space, that is,
One question is here about scalar multiplication properties.
yes,
Is
yes.
there any additive property between scalars of field elements? Like in first part, you have said that like
You are right.
multiplication between A and B. Is there an yes, sir, additivity A plus B like that distribute is held?
Yes, yes, you are absolutely right. Forward.
Okay.
So this needs to be satisfied. So Rn is a field. Similarly, takes complex numbers. Cn is a field over R. And another example will be like this: complex number C is a field over R, or any field F over F. It is always a vector space. The scalar multiplication is same as the multiplication from the field. There are two multiplication. Note that there is two multiplication. One multiplication for the field, and another multiplication is the scalar multiplication. Okay. If you take F over F, field, that is real number over real number, then it is also a vector space. Let us see some example. First question is that those are true and false. Every vector space contains a zero vector. Is it true or false? So this is true. Every vector space, yes, because it should be abelian group, and abelian group always contains zero. By definition, it is true. A vector space may have more than one zero vector. Is it possible?
But sir, excuse me,
Yes.
if the operation is different from addition, then zero vector may be exactly equal to zero. There may be some another identity element other than zero. It totally depends on operation, I think so. If we take unusual operation other than addition, then it may not be exactly like zero. It may be another element, but
What you
we
are
say that element is identity.
Yes, what you are saying is, you said is true. That is zero with respect to addition. Okay.
Yes, sir, but
Zero
I
here the notation zero is the notation only.
okay, okay,
It
okay,
is not the same as zero.
okay.
Yes, you are right, correct. A vector space may have more than one zero vector. Is it true?
Yes, sir.
No, it
No,
cannot.
sir. because identity must be unique, I think so.
Yes. So suppose 0 and 0 dash, or suppose 0 dash, those are two zero vector. We'll prove that these 0 and 0 dash are same. How can we prove? So first, assume 0 dash is the 0 vector. Then 0 plus 0 dash is same as 0, because adding with 0 dash, this will give same 0. This will give same element. Okay. Now if you assume this is 0 vector, then adding with 0 does not change anything. So it will give 0 dash. That is what you got. You got that 0 dash is same as 0. So we have chosen two different 0. Not two different. We have to chosen two 0 dash. If possible, 0 dash to be different. But we have seen that it is not possible by the property of 0 dash. Okay, by the property of 0. Let us see the third question. In any vector space Ax equal to Bx, does this imply A equal to B? Can we cancel X?
No, sir. If x is 0, then we can't.
Yes,
X must be invertible in
yes,
that sense.
you are correct. It is not true, because A times 0 is same as B times 0. But A and B can be different. For example, take A equal to 1, take B equal to 2. So it is false. But suppose the condition, another condition is given. Suppose X is non-zero. If X is non-zero, then Ax equal to Bx. Does this imply A equal to B? Now what will be the answer?
Yes, sir. If x is non-zero, then we can say inverse must be exit. So we can take out inverse from both sides, multiply by x inverse, and x and x inverse compose, and we get identity element from that part. And in left hand side we get a into identity, that is again a, and in right hand side
Yes,
we get b into identity, that is.
what you are saying will be true for the second case. That is X equal to AY, the second question, and given A is non-zero. Then you can multiply A inverse on the both side. So A inverse times AX equal to A inverse times AY. This will give X equal to Y. What you are saying will be true for the next question, D. But for this question, your argument will not work. Because in vector space, there is no multiplication structure. That is, V does not have any multiplication with. So take X, Y belongs to V. You cannot multiply X with Y. The multiplication will work for the scalar field. For example, suppose consider this vector space R3. So there is a vector 1, 2, 3. There is another vector, suppose 0, 1, 2. So you cannot multiply those two things in R3. Okay, you cannot multiply like this. So your argument will fail for this case. But still it will be true. How? So given Ax equal to Bx, then you can write Ax minus Bx equal to 0. Then it is same as A minus B into X equal to 0. Suppose A and B not equal. It is suppose. Okay, sorry. Okay. Yes, your argument will work for this also. Suppose A not equal to B, then you can take inverse of AB, A minus B. This will gives X equal to 0. Yes. Your argument will work, but the problem is you cannot invert the element from the vector space. Okay. You cannot invert X. You can invert A minus B. So this is a contradiction. So if X not equal to 0 given, then A and B must be same. Is it clear, everyone?
Yes, sir.
Oh, great. So this is also false because A can be 0 by the same reason. Consider this question. Uh, so V is order pair of real number, that is V is same as R2. But here the addition and multiplication is not what you usually see. That is, it is not pointwise addition and pointwise multiplication. Okay. R2 forms a vector space is if the addition is like this. Addition must be like, not must be, but if addition A1 plus A2 and A1 dash comma A2 dash, if this is same as A1 plus A1 dash comma A2 plus A2 dash, that is we are adding pointwise. And similarly C times A1 A2 is same as C times A1 comma C times A2. You can check that all the properties are satisfied by those addition and multiplication. Therefore, this is a vector space. R2 is vector space under this addition and operation, under this addition and multiplication. Okay, over R itself. The field is R, but the problem is uh, here the addition and multiplication is not the natural addition. Now, what is your guess? Will it satisfy all the property of the vector space or not?
I think, sir, there may be problem in scalar multiplication part.
Scalar multiplication part, there might be a problem. So
Mm.
let us see. Because we have seen that 0 times, in the previous question we have seen that 0 times a1 comma a2, this should be 0 times some vector, 0 dot some vector. It should be which vector? 0 times some vector. What will be 0 dot v? It is always 0. Okay. So here you can see that 0 times a1 comma a2, by this definition it will be 0 dot a1 comma a2, which is same as 0 comma a2. But 0 comma a2 is non-zero. It is not same as 0 comma 0. We can choose a2 to be non-zero. For example, choose a1 equal to 1 and a2 equal to 1 also. Then you can see that 0 comma a2 is not 0 comma 0, because then in this case it will be 0 comma 1, which is not same as 0 comma 0. So yes, Swati, it is true. What you are saying is true, that multiplication, there is some problem in the multiplication. So answer is no, it is not a vector space. Moreover, it will be not even an abelian group, because what you can see that adding with 0, 0, add a1 a2, add this thing with 0, 0. This will gives a1 comma a1 dot a1 by this definition. This will be a1 plus 0 comma a2 into 0. This is same as a1 comma 0. So not only multiplication is problematic, addition is also problematic, because adding something with 0, this should be same, but you can see that it is not same as a1 comma a2. You can choose a1 to be 1, a2 to be 1 also. Is it clear? Addition and multiplication does not satisfies the criteria of to be a vector space. So let us see the third question. Here V is,
But sir, identity may not be zero in previous case because let's say identity is ordered pair of e1 comma e2. Then we apply standard operation a1 comma e2 plus e1 comma e2 is again must
yes,
be equal to a1 comma e2, and from that part we will get value exact value of e1 and
yes,
e2. Then how can say initially 0 0 will be our identity
yes.
element in this
What
case?
you are saying is true. Here the identity will be 0 comma 1. Yes.
Yes, sir.
Then I can't use this way, because then it will be same as a1 comma a2. But still, addition, is it a, yes, addition is not problematic. Yes, under addition all the properties will be satisfied, because hmm,
We can check
but
commutativity
there will be
property.
problem
Maybe
for
some
inverse.
problem.
Uh, what are you saying?
Maybe there will be problem in inverse and commutativity property. We can check.
No, there will be no problem for commutativity, but inverse will be problematic. Why? Because uh, take an element 1 comma 0. You cannot find the inverse of 1 0, because suppose there exists an inverse. Suppose 1 0 has an inverse. Okay, so let 1 0 has an inverse. Suppose a comma b be the inverse. Okay, ab, then 1 comma 0 times uh, sorry, add a comma b. This should be the identity, additive identity, which is 0 comma 1. But from the definition, how do we add? It is like 1 plus a and multiply 0 with b. This is same as 0 comma 1. But you see that 1 plus a equal to 0, this is fine. But the second thing is 0, and here the second thing is 1, which is which will imply 0 equal to 1. It is not possible. Okay, therefore there is contradiction. So it cannot be a vector space. Even it cannot be a abelian group. Is it okay?
Yes, sir.
Okay, great. So let us see the next question. Here the operation is C times A1 comma A2. It is A1 comma 0. Now what can you say?
No,
Yeah.
sir. This is not a vector space. Clearly, again, scalar multiplication property 1 into v must be equal to v. Here, if I take c is equal to 1, then if 1 into a1 comma a2 is not equal to again a1 comma a2 is according to given operation. So due
This
to
is
this property, rejection of this property, we can say this is not a vector space.
because for vector space multiplying by 1, this should gives the same element. But what can we see that it is not correct. Multiplying with 1 does not give the same thing. So yes, it is not a vector space. Yes. Now there is sequence of real number. Do you know what is the meaning of sequence? Sequence will be like,
Sequence is basically a function whose domain is set of natural numbers.
yes. So we can write n to be a1, a2, a3, and this will continue forever. So all AI belongs to some field. For example, you can take the field to be R for your convenience. So there are two sequences, AN and BN. You can add by this natural way. That is, you can add pointwise, as similar for Rn or for V to the power n, any vector space to the power n. So the question is, will it be a vector space? So let us check all the operations. So addition should satisfy associativity. An, Bn, then add Cn. By definition, it will be same as An plus Bn, then add Cn, and this is same as, again by definition this will be same as An, Bn and Cn, but adding three real number. This addition is associative, so we can write in this way. And now you can separate n.
Sir, is there any disturbance in case of negative number, in case of associativity? Maybe.
So for associativity, it is working. Okay. So will there be any problem for identity, additive identity? What will be 0 for this case? Any guess? What will be 0?
Yes, sir, 0 will work here for additive identity.
Yes. You can take 0 to be this sequence. 0 everywhere. So 0 exists. And what will be then additive identity? What will be additive and identity? Minus of some, take an element n from this sequence. What will be additive inverse of this? It will,
Additive inverse will be negative of that particular number.
yes, you can take minus a1, minus a2 everywhere, minus an. So with respect to addition, everything is okay. Therefore, v, this v with respect to addition, this is abelian rule. I have not checked the commutativity yet, but you can see that an plus bn, this is same as bn plus an. So it is okay up to abelian group, everything is okay. Now we need to check other properties. Will it hold? For example, scalar multiplication need to be associative, and it need to be distributive, and multiplying with 1, this will gives n. What will be the 1 multiplicative identity? So take 1 belongs to the real number r or the field f, whatever. Then you can see that 1 times an, again pointwise multiplication, this is same as an. So multiplying with 1 will give the same thing, but what about distributive property? That is, take two scalar k1, k2 and multiplying with an, it will be same as k1 plus k2, then an, but this is same as k1 times an plus k2 times an by distributive property of real number. But this is same as, you can separate now, k1 an plus k2 an. So all those properties are satisfied. Uh, this is distributive property of one side. Another distributive property will be n plus bn. Now multiply it with a constant scalar k. K belongs to the field R. So you can see this is same as, first add an bn and then multiply k. But this is same as k times an bn. Now distributive property of real number, this will gives k times an plus k times bn. You can separate now. So take k outside. So now you can see that all the properties of multiplication is working. Scalar multiplication, all the properties of scalar multiplication is working. So you can say now v addition with the multiplication is vector space. So it is true. Is it clear, everyone?
Yes, sir.
So sequence with pointwise addition and pointwise multiplication is a vector space. The all the checks are similar to the real number up to the power n. Okay. So now let us remove this. So here V is a vector space, W is a subset of V. That is also a vector space. Then W is subspace of V. What is the definition of subspace?
If
Itself
under
a
the
vector itself a vector space under the same operation and same binary.
operation,
Yeah.
yes, sir, and field must be same also in that case.
Mm. So given a vector space V plus dot, this is a vector space over field R or F, suppose. And now W is a subset of V, and subset of V means W satisfies all the properties of V. But first we need W to be closed under addition and closed under scalar multiplication. And closed under scalar multiplication. Then we say that W is a subspace of V. Okay. Then W is a subspace of V. So for this question, by definition, it is true because whenever W is a subset and W satisfies all the property of vector space, it will be a vector space itself. So it is true. What about the second? The empty set is a subspace of every vector space. Is it true?
Yes, sir.
No. Vector space has at least one element, 0, but empty set has no element. Okay,
Yes, sir.
Yes,
so it is
yes.
false. If V is a vector space other than the 0 vector space, then V contains a subspace W such that W is not equal to V. Is it true? A non-zero vector space must have a smaller subspace. Is it true? 0 is a vector space. Take only 0.
Yes, sir. 0 is a vector space.
So,
Then we can take W equal to 0.
take W equal to 0. This is a vector space. And you see that W is also strictly smaller than V. So it is true. What about the next question? The intersection of any two subset of V is a subspace of V. Is it true?
No, we have property intersection of two subspaces of V is again a subspace, but we can't say about
Yes,
subset.
because those subset may not form a vector space. Okay. For example, take 1 and 2, or suppose 1 and 4. Those are two subset, but their intersection is non-empty. Their intersection is empty. Therefore, it is not a vector space. It is false. There are a few questions. You need to check those A, B, C, D, E, F. All those are vector spaces. So first question, W1, is it a vector space? A1,
Yes, sir.
how can you say that this is a vector space? That is it a
Linearity and identity element.
Yes.
Yeah.
So how do we check a vector space to be a subspace of another? Suppose V containing W. How do we check, or other way? Suppose W containing V. How do we check W is a subspace of V? So take any two element W1 comma W2 from this W, then W1 plus W2 must belongs to W if it is a if it is closed under addition, and take any C from the field F. Now if multiply W1, if it is also belongs to W, that is closed under scalar multiplication, only those two properties will guarantee that W is a subspace of V, because other properties are hereditary. Other properties, for example, scalar associativity or zero, those property will be satisfied automatically. Okay, so we only need to check those two property, but instead of W1 plus W2, yes, it is okay, because for vector space -1 also exists. Okay, for from the field -1 always exists. You can add W1 minus W2, that is W1 plus -1 times W2. So we need to check only those two conditions. For A, is it working? For A, is W1 closed under addition and scalar multiplication? So take two element, let A1, A2, A3.
Yes, sir. W1 is closed under addition and scalar multiplication also.
Okay, great. So let us check those two elements from R3. Now, those two elements from W1. Now we'll check that their addition must be in W1 and their scalar multiplication must be in W1. So add those two elements. So what is the meaning to be in the W1? To be in W1? What does this mean?
For W1, along with these three tuple properties must be satisfied. Like if we take A1, A2, A3 first element, then A1 must be equal to 3A2. So we can write at place of A1 3A2, and like that at place of A3 we can write like minus A2.
Yes, you are right. So we can write those two things. Now, what about addition? So adding those two will give A1, A2, A3. Add it with the second tuple, which is same as pointwise addition, A1, B1, A2, B2, A3, B3. So those tuples will clearly belongs to R3, because ABC, those element AB are the element from R3, real number. Now we need to check if it satisfies this property. That is, first entry should be 3 times the second entry, and the next thing. So here the first entry is A1 plus B1. But using this equation, using equation 1 and equation 2, you can write A1 equal to 3A2, B1 equal to 3B2. And this is same as 3 times A2 plus B2. So first property is working. Now we need to check the second condition, A3 equal to minus A2. Let us check. So in this case, what is the third entry? Third entry is A3 plus B3. But again, if you use 1 and 2, then A3 is same as minus A2 and B3 is same as minus B2. So this will give minus A2 plus B2. Hence, it is closed under addition. Therefore, W1 is closed under addition. In a similar manner, take K to be any real number. Okay, the field is a real, so take K to be any real number. Now multiply K with A1, A2, A3. This is same as KA1, KA2, pointwise multiplication. Now after that, you can write, that is, we need to see if those two conditions are satisfied or not. So K1, you can write A1 equal to 3A2 from this. So it is same as K times 3A2. But associativity of scalar, this will give 3 times Ka2. Also, you can write Ka3, the last entry. This is same as K times minus A2. But again, associativity of scalar will give this is same as K minus Ka2. So therefore, you can see that it is closed under scalar multiplication also, because it satisfies those two properties. Okay, if you add two vector, it satisfies this property. If you stretch this vector by some constant k, then it also satisfies this property. Geometrically, it is saying that those two vector will lies on the same plane. Then addition of those two vector must lie on the same plane. And if you stretch the vector, it also must lie on the same plane. This is geometric interpretation. And we see that it is working. Therefore, W1 is closed under scalar multiplication. Therefore, the conclusion is W1 is a subspace of R3. So, in the similar way, you can check W2 is also subspace and W3 is also subspace. B, C are true. D is also true. That is, any linear equation will give a subspace. Okay. This linear equation will give a plane which passes through the origin. And any plane passes through the origin must be a subspace. You can check all the properties are satisfied. So what about E? Is it a subspace? It is also a plane, but is it a subspace of R3?
No, sir. 000 is not doesn't satisfy.
000. This additive identity does not belong to W5, so it cannot be a subspace. Okay, therefore,
What about W2, sir? 000 in this case.
What about
This,
W2?
yes, sir. I think
Yes,
it is
it is
also.
also not a subspace because it does not, the plane does not passes through origin. Yes, it is not a subspace. What about F? For F, 0, 0,
Uh,
0,
000 satisfy,
that is
but linearity doesn't satisfy here. So
okay.
I
Let
think
us check if linearity is satisfied or not. Okay. Instead of linearity, let us check scalar multiplication because it is easier, much easier. So for F, 5a1 square minus 3a2 square plus 6a3 square. Let us do a new slide. Okay. So for F, it is the subspace given by those three equations. Can you suggest a point which belongs to W6? A vector which belongs to W6? A point. Can you give me a point which belongs to W6? For example, take A1 equal to 1 and take A2 equal to 1. Then what will be A3? So let us check what will be A3. 5 into 1 square minus 3 into 1 square plus 6a3 square is same as 0. That is 5 minus 3 which equal to 2 plus 6a3 square equal to 0. But this is same as a3 square equal to minus 2 by 6, that is minus 1/3, and a3 is equal to here the problem is it is negative. So instead of a2, choose a3 equal to 1. Okay.
we can take in fractions because
Okay, let us see in this way. 3a2 square and 6 a3 square. A3 square means 1 square. So for this case, it will be 3a2 square is same as 11. Now a2 is same as 11 by 3, square root of this. So an element of f will be 1 square root of 11 by 3 and 1. This belongs to W6. But what about scalar multiplication of this element? For example, multiply this element with 2. Multiply, suppose v with the scalar c equal to 2. Then what is c times v? It will be 2 comma 2 root 11 by 3 comma 2. Now thus does c dot v, this satisfies the equation, the condition, does C dot V satisfies this condition? Let us see. 5a1 square minus 3a2 square plus 6a3 square. Which is same as, okay, here the scalar multiplication will work because it is homogeneous, actually it will work. Scalar multiplication will not help. Okay, so you need to choose another point. Another point.
Sir, we can talk about closure property like A1, A2, 3 tuple, A3, let's belong to WF,
Yes.
and another paired B1, B2, B3, and maybe some addition because we know that A plus B whole square is equal to A square plus B square plus 2AB. So maybe that 2AB part must be
Must,
disturbed
must
condition.
be 0. Yes. Yes. What you are saying that we can can use this, that W6 is not associative. Okay. W6 with the operation addition is not associative. Why? Because you can choose those two elements and you can see that no associativity will work. Everything will work, but it is
Closer
not
property.
closed. Why? Mm, because we need to cancel those product term a1 a2 a1 a3 etc, but this does not guarantee because you need to prove that it is not working. Okay, that is, you have to give an example which shows that it will not work. Sometimes we cannot see the structure. Okay, that's why you need to prove that there exists an element for which this is not working. That's why I have chosen an element P. So you need to choose another element.
Sir, like in the last thing, what you did, you took another point B1, B2, B3. Same
Yes.
thing we can do here also, no?
For which
Uh,
question?
the sheet which you put in some other place, no, that sheet we had, like we took 2 points, A1, A2, A3, and then B1, B2, B3.
Yes.
So if we put B1, B2, B3 and then evaluate it, squares will not be close like
Yes.
that under
What you are
addition.
saying is true, but for which we need to give an example for which the thing is not working. Okay. So let us try by your way. Mhm. So take 2 points.
So we can take another example 1 minus square root of 11 by 3 comma 1.
Yes. So let us check by the way suggested by both of you. So take those 2 points from W6. Now suppose this is V and this is another vector W, or this is V1 and V2. So what will be V1 plus V2? It will be scalar of pointwise addition A1 B1, A2 B2 and A3 B3. So those V1 V2 satisfies this equation, but is the addition will satisfy this equation? So this is the question. Let us see. So 5 a1 plus b1 square, 5 times first entry square minus 3 times second entry square plus 6 times third entry square. Is it 0? This is the question. This is the question. If it is 0, then we are done. That is, this system is closed under addition. But if it is not 0, why it is not 0? Why is it not 0? We have to check. This will gives, sorry, this is same as 5 a1 square minus 3a2 square plus 6a3 square, and similarly 5b1 square minus 6b2 square, 6b3 square. Those two things will be 0 because v1 v2 belongs to w6. Any element from w6 satisfies those property. But what about those extra term? That is 10 a1 b1 minus 6 a2 b2 plus 6 a3 b3. The problem is this may not be 0 always. This
12
may not be 0.
B3.
What?
12a3b3.
12. Yes. It will be 12. This may not be 0 for all those points in W6. This is the main thing. But you need to check that for all points in W6, this condition is not satisfying. Okay. You cannot say from this that it will be not true. Because for which values? Question is for which values of a1, a2, a3 and b1, b2, b3 this is non-zero. This is non-zero for which values? That's why you need to take two elements such that they lies on the space W6, but their addition does not lie in this space W6. What your guess is true, but the problem is we need to prove rigorously that yes, in fact, it is true. Is it clear, Swati?
Yeah. So this is a general approach to such problems that to prove that they're closed under addition, we take 2 points.
Yes.
And to prove that they are closed under scalar multiplication, we take multiply by k and then see if we can prove it is satisfying this equation.
Yes.
Okay.
But if it is not true, then you need to give an example for which it is not holding. Okay. So,
Sorry, can you say that again? So if say we got
here it is not done.
Yeah.
Question number if it is not done yet. You need to give to V and W for which this satisfies, but their addition V1 plus V2 does not satisfy this equation.
Okay, so we have to give two
Explicitly, yes.
Two vectors.
Yes.
Which will prove this. Okay.
Okay. So I am not doing this because it will consume lots of time. So it is exercise for you. Exercise. Now find V1, V2. For which V1, V2 satisfies those that equation, but V1 plus V2 does not satisfy this same equation. So there are few questions about subspace. Question number 1. W given by this equation, is it a subspace? W given by this. So we are taking all polynomial PF denote polynomial over F, or polynomial over, for example, you just take polynomial over real polynomials. So question 1 says, take W the subspace. We don't know is it subspace or not.
It is not a subspace because if we take two polynomials and in first polynomial all terms are positive and in another polynomial some terms are same but differ by sign, then degree may not be same like n of some summation of those two polynomials. So degree will disturb the subspace
Yes,
property here.
degree will disturb, but you need to give an explicit example. So can you give two polynomials such that their sum does not belongs to W, or their
Yes,
scalar?
sir. If I take small n is equal to 2 and first polynomial is like x square plus 2x plus 2 and
Yes,
second polynomial is minus x square plus 2x plus 2, then sum is equal to 4x plus 4 and the degree of this polynomial is equal to 1 and so is it doesn't satisfy this condition, so it will not be a subspace
yes.
of this particular polynomial.
What you are saying is completely correct, but you cannot choose n, okay? Because n is given anything. You cannot take n to be anything. So
Okay, sir. So we in this case we can say like x raised to power n, and in another case we can take minus x raised to power n, so that this part will be cancelled out, and the remaining part may be of degree may be equal to n minus one or maybe less than that part.
those two elements are from W, but F1 plus F2, it is same as 4, but 4 does not belongs to W, because W is the space for which either fx equal to 0, that is either the whole polynomial is 0 or fx has degree n. But here we see that fx has f1 plus f2, it has degree 0. It is not degree.
Sir, can you, to understand the question once again, like can you read how do I read this question? Like, is the set W
Yes,
space of polynomial? What is P of F? How it is read?
pff means polynomial space, that is entries will be like one any polynomial. You can take a0 plus a1x plus
Okay.
anx to the power n.
Okay, so it says that the set W is a function f of x, which can be any polynomial function. Is that what it means?
Yes, pf is the any polynomial. Pf,
Yeah. So f of x is belongs to that polynomial, any polynomial. It can. Okay.
fx here the condition is either the polynomial is zero polynomial, that is whole polynomial is 0, or
Okay.
f should have degree n.
Okay. So n can be anything. That's what the question is saying, right?
Uh,
Just trying to understand the question. So it is saying that f of x has a degree n. Uh, is then
no,
is
n is constant, whatever uh,
okay.
they have assumed. For example, there can be n equal to 2 also.
Okay. So is the W a subspace of does W belong to the subspace of this polynomial function?
Hmm.
Okay.
Is W a subspace? We see that W is not closed under addition.
Okay. Okay, because we took two different polynomials and
Degree
when
n,
we added
what?
them, it was not of the same order in the
Yes.
same. Okay.
So now the question number 2, And the question here it is saying that all upper triangular matrix. Okay, is it a subspace of matrix? So the question is like this. We know that M cross N, that is M by N matrix, those matrices form a vector space. But the question is upper triangular matrix, here it is denoted by so it suppose W is all upper triangular matrices, set of all upper triangular matrices. So clearly W is a subspace of M cross N, but is W closed under addition and closed under multiplication? Is it true?
Yes, sir.
That W is, so let us see. Yes, what you are saying is true. Upper triangular means below everything will be 0 and there will be some terms a1 1 up to a1n. Similarly, it will be a21 then a2n. Okay, the last step will be an comma m comma n. And similarly add another matrix b11 up to b1n, 0 b21 up to b2n, and continue this. You can see that addition is also a upper triangular matrix. It will be a11 plus b11, then a1.
These terms are B22 and corresponding matrix term is A22 because A21 and B21 is 0.
Yes, bm. What is the doubt? Is there any doubt? Sorry.
No, I didn't say anything. I think someone else was.
Jyoti, what are you saying?
In first matrix, A21 is 0 because
Oh, sorry. A22.
and B22.
It must start
Yes.
from 2 to second position. Okay, sorry. Okay. So we can see that sum of two upper triangular matrix must be upper triangular matrix. Similarly, you can see that some scalar times this upper triangular matrix a11, a12 up to a1n, 0, a22 up to a2n, and dot dot dot. It will be 0, 0, ann. This is the upper triangular matrix. Okay, so you can see how the triangle forms. This is same as k times a11 up to k times a1n, and here it will be k times an. It is also upper triangular. Below that everything will be 0. So the second thing is true that W is a subspace.
So this, if we are saying W is a subspace, then it means that it belongs to the same space as the original space.
Yes,
Right?
you are saying that uh, you have chosen two elements from W, and you are proving that their addition and their scalar multiplication also belongs to W.
Okay.
Closed under addition, and the second will imply closed under multiplication. That
Yeah.
is
So here, what is the criteria? Because the result of addition and result of multiplication is also a triangular matrix.
yes, also a triangular matrix.
So that is the criteria for
That is
closure.
the criteria for closure. Because
Okay.
W is defined in this way. Take all upper triangular matrices.
Okay. Okay.
Great. So question number 3. So those notation are pretty bad, but let us take some simple notation.
One request: can we read the question before starting? Because
Okay, sorry.
Mhm.
It is my mistake.
No, it's okay. I mean, we just want to take some few seconds to read and
Yes,
then.
yes, yes. So third question says take all function. Okay, S is non-empty set, F is filled, and S0 is a point from S. For example, choose S to be R itself. So we are taking all function instead of S. Let us use this notation. Instead of S, let us use the notation X because it is more familiar to use this notation. So we are taking function from X to F. This notation denotes all function from X to F. X to real number, X to some complex number. And this is the function space. All function from X to that field.
So the question is not very clear.
Question will be like this. So instead of this question, let us simplify this question this way. So three. Take F from R to R. This is the space. This is the given vector space V. All function from real to real. Okay. Is it clear? What is the definition of F?
Mhm. Yeah. Yes.
The sub W, we don't know yet if it is subspace or not, but W is defined in this way. Take all function from R to R, that is all function from this V such that F vanishes at some point. For example, F vanishes at 1. Now the question is W a subspace of V or not? Those function space form a vector space. Okay. The question is W a subspace or not? That is all function.
Yes, sir. W is subspace because closure and scalar multiplications properties are held here.
Okay.
If we take two functions like g is another function from R to R and g must be satisfied this condition. So value of g at 1 is equal to 0, then sum of those two functions f plus g must be from R to R and f
Yes.
plus g will be
Write
equal.
what you are saying. So choose two functions fg from W. So what is the property of fg? By definition, f at 1 should be 0, g at 1 should be 0. But now let us check. So f plus g, this is also a function from R to R because you can add those function by pointwise addition, fx plus gx, and you can multiply f in this way. If you multiply with some scalar k and evaluate, it will be k times fx. This is how you can multiply and add two functions. Okay, that is scalar multiplication and addition. K belongs to R. So does f plus g satisfies the criteria? This is what we need to check. Does A plus G satisfies the criteria?
Yes, sir. We can find out value at 1.
It will be
So,
same as, by definition, it will be same as F1 plus G1. But this is same as 0 plus 0, which is G. So we see that F plus G belongs to W. Similarly, K times F of 1. This is also same as K times F1, which is K times 0, that is 0. So K times F also belongs to W. So W is closed under addition and closed under multiplication, scalar multiplication. Therefore, W is a subspace. Swati, is it clear?
Yes, sir. So we have to find example also. If we have to give exam, then that time we have to give example also.
Here it is not a example.
No, it is not. But in like in the exam, when we write exam, that time we have to give points also, real function, like real points.
No, it is not that thing. I, I have just simplified that this question. Instead of real, there is x. Instead of real, there is x, and the field is any field. Not,
Okay.
but same thing will work, because
Okay.
take f and g from this function space and add a plus g, evaluate at s0.
Mm-hmm.
What will be this? This will be same as f at s0 plus g at s0.
Mm-hmm.
But by definition, this will be 0.
Mm-hmm. Okay. Mm.
So there are few questions. So let us uh, cancel this question because we have shortage of time. Let us try question number 5. So differentiable real valued function. You know about differentiability and continuity. So here CR is the space of all continuous function. Okay. So there are spaces. One space is set of all functions, but instead of all function, we can restrict to continuous function. Now, instead of continuous function, we are restricting on differentiable function. That is, here V is CR, set of all continuous function, and W is W equal to differentiable function. This is W. Now, what can you say? Is W a subspace or not?
sir, basically here W is not a subset of V because like modulus function, these are continuous function but not a differentiable function at 0. So the V set must be superset of W, but differentiability is a broader criteria than continuity.
Yes. Nini.
But uh,
Previous question where we concluded that it was not a subspace, but here we say it is subspace. Ravi, can you say it again? What are you trying to say, Ravi? Okay, Nini, as she asked, example, what is the exam pattern? MCQ descriptive mark distribution. Sir, question 1, is it similar? Question 1, is it similar to question 3? No. Yes, the function space is similar because polynomial function are special cases of the function space, but here there will be more function. Okay, there will be lots of function. For example, sine, cosine. This is the difference between question 1 and question 3. Question 1, it was not a subspace, but question 3, it is subspace. Yes. So let us. Question 5, it says W is subset of continuous. So you know a differentiable function is always continuous. Do you know this?
Yes, sir. Every differential function is continuous. So
Yes. So W is a subset of V. It is okay. Now you have to worry about closed under addition and closed under multiplication, scalar multiplication. So if you add two functions, two differential functions, two differentiable function, if you add those two things, will it be differentiable?
Yes,
yes,
sir.
sir.
Sum of two differentiable is again a differentiable
Yes,
function.
Ravi, it is true. Jyoti, it is true. And if you multiply with some scalar, suppose multiply with 2 or 3 or any scalar you take, will it be differentiable?
Yes, sir.
Yes. So now what is your answer? So you have seen that addition of two differentiable function is differentiable. Scalar multiplication of two differentiable function is differentiable. So
I think it will make a vector space.
yes, therefore it will make a vector space. So for 5, yes, it is a vector space. That is a subspace. Because addition of two differentiable function is differentiable, and similarly scalar multiplication. So it is true. It is a big question. Okay. So instead of reading the whole thing, I just provide the definition. For now, let us avoid this question. So you know about skew symmetric and symmetric matrix, right?
Yes.
Then the question says, uh, let us rewrite the question. Does M cross N is same as direct sum of symmetric and Q symmetric? Let us denote the symmetric matrix by W1 and the space of skew symmetric matrix is W2. Symmetric and skew symmetric. So what is the meaning of symmetric and skew symmetric matrix? So suppose A is symmetric, then what is the property? What is the definition?
Sir, on previous slide, here you write matrix is a direct sum of symmetric and skew symmetric.
Yes.
But I think it is not right because for this property, W1 and W2 must have Disjoint means only zero matrix must be common matrix of there, but here any diagonal entries may be their intersection part.
The problem is skew symmetric matrix does not have any diagonal entry because every skew symmetric diagonal entries will be 0
Uh,
by skew symmetricness. That is what you have not noticed. So let us.
yes, 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 yes.
So definition of symmetric means A transpose equal to A, and similarly B is skew symmetric. This means B transpose equal to minus B. And what is the meaning of direct sum? Direct sum means, so suppose W1 and W2 be two vector space. So we can define their sum W1 plus W2 in this way. It will be some small w1 plus small w2 such that w1 comma w2 belongs to w1 plus w2. Now, moreover, the thing is that this w1 plus w2 forms a vector space. You can check all the properties. So it will forms a vector space. Therefore, uh, we denote it by, we say it sum of vector spaces. But moreover, if the intersection, if w1 and intersection w1 intersection w2 is only the single 0, because 0 belongs to every space, so it cannot be empty. There is at least 0, and if it is at the 0, then we say this sum to be direct sum. We denote it now, this w1 plus w2, this is denoted by w1 direct sum w. So here, can you write every matrix as sum of symmetric and skew symmetric matrix? Suppose X is any matrix. X belongs to Mn cross n. Can you write X as sum of symmetric and skew symmetric matrix?
Yes, sir.
Yes.
With the help of transpose of matrix.
Yes. The usual tree, take X plus X transpose and X minus X transpose. So let this is equal to w1, this is equal to w2, small w1, small w2. Then you can see that w1 transpose is w1 and w2 transpose, yes, yes. So yes, Ravi, true. Therefore w1 is a symmetric matrix. W1 belongs to big w1 and w2 belongs to big w2. Hence now you can say X is, that is instead of X, Mn cross n, this is sum of symmetric and skew symmetric matrix. But when will it be a direct sum? What is the condition? we need to check that intersection of W1, W2 0 or not. Yes. So let us take an element from the intersection. So let suppose C belongs to the intersection of W1, W2. Okay. Then what can you say? C belongs to W1. Mean W1 is same as W1 transpose. C belongs to W2. Sorry. This means C equal to C transpose, and this means C equal to minus C transpose. Therefore, C transpose is same as minus C. Therefore, C is same as minus C. And hence, C equal to 0. Okay. So, now you can say that every element from the intersection will be 0. That is W1 intersection W2 is 0. Therefore, n cross n matrices is direct sum of W1 W2. Is it clear?
Okay, sir.
Okay, great. So let us see some example from basis and dimension. Okay.
Sir, how I can collect the class notes?
I have shared a folder, na? Have you seen that folder? YouTube link and folder.
No, sir. No.
I have shared a an YouTube link and a folder. You just any textbook. You can use this Hoffman Kunze. There are several textbooks for this course. Hoffman Kunze, or you can take Sheldon Isler is not good for starting, but Gilbert Strang, it is also a popular book. And another very useful book, it will be by Friedberg. Yes, Friedberg, it is easiest way to start, and Gilbert Strang is also it is very easy to read Gilbert Strang. So you can choose 2 or 3, or by I.K. Rana. Professor I.K. Rana also has a book for this course. So, what is the definition of linear independence? Suppose V1, V2 up to Vn. N vectors belong to V. When those vectors will be said to be linearly independent?
If all the scalars are 0.
That is, their linear combination is 0. This will imply all scalars are 0. C1, Ci belongs to scalar. Those are from field. Okay. So this is the definition of linearly independent. When and then we'll say V1 up to Vn are linearly independent. So here the question is 1 2 3 0 1 2 and 1 1 1. Are those three vectors linearly independent? No, sir. Yes, you are right. But why it is not linearly independent? So
Because sum of last two vector is equal to first vector, so we can choose scalars other than 0.
here you can see 1 2 3 is same as sum of 0 1 2 1 1 1. That is same as v1 is sum of v2 plus v3, and this is same as 1 dot v1 minus 1 dot v2 minus 1 dot v3 equal to 0. So there is a non-trivial linear combination such that the linear combination is 0. Okay, that is, though the linear combination is 0, but the scalar are non-zero. Scalar is not 0. That is, there exists a non-trivial linear combination for those three vectors. So v1 v2 v3 are not linearly independent. What will you say for this?
They are linearly dependent.
Yes, therefore v1 v2 v3 are linearly dependent. Okay. There is another question. So linear independent, it is clear. Now, do you know about span? So given vectors v1 up to vn from v be the vector space. Span of this set, suppose yes, you are right. So span of this set is linear combination of those vectors cv1, c1 v1 up to cn vn, where ci are from the scalar. You can see that this span is also a vector space. Okay. For example, m n cross n be the vector space. Let us consider this is the vector space. Can you give a spanning set for this?
Place one and at A11 and all other entries are 0, and in similar case put A12 equal to 0
Yes.
and all other entries are like standard basis.
Yes. So standard basis will work. E11, E12 up to E1n. Similarly, and everything that is spanning set is equal to Eij, where I equal to 1 up to n and j is also 1 up to n. Because any matrix A11 up to A1n and AN1 up to ANN, you can write it as A11 times 1 and everything is 0. Okay, plus A21 or A12, second position is 1 and everything is 0. Up to you can continue this to ANN, everything is 0 except the last entry. Therefore, S span V. You can write V as span of S. Is there any question? Okay. So there is an interesting question. So before that question, what is basis? What is the definition of basis? Basis.
Basis is basically a subset of vector space which satisfy two conditions. First, the vectors must be in basis are linearly independent, and that set must span the whole vector space. So, it is a spanning linearly independent set.
Yes, it is a spanning set. That is V. Any vector of V can be written as linear combination of S. And the second condition, S is linearly independent. If those two properties are satisfied, then we will say S is a basis. So question, can 0 be a basis?
No, sir. Zero is not a linearly independent.
Yes, you are right. 0 is not linearly independent. That is 1 times 0, it is same as 0. So answer is no. There is a question. So alpha 1 equal to 1 0 minus 1, alpha 2 equal to 1 2 1, and alpha 3 equal to 0 minus 3 comma 2 is, that is alpha 1 alpha 2 alpha 3. This set is a basis for R3. How will you check this if it is basis or not?
So, firstly, we check linearly independence, maybe by basic definition, or maybe determinant of matrix.
Yes.
And another is spanning set, so we can take arbitrary element from R3 like 3 tuple x comma y comma z, and we try to write this tuple in form of C1 alpha 1 plus C2 alpha 2 plus C3 alpha 3, where Ci belongs to R, that is field, and
Yes.
if
What you are
we
saying is true. Let us do. So what Jyoti is saying is true, but let us check. So first we need to check linearly independent or not, Li or not. Okay. So let C1, C2, C3, 3 scalar from R. Now C1 alpha 1 plus C2 alpha 2 plus C3 alpha 3, this is 0. This will imply C1 times 1 0 minus 1 plus C2 times 1 2 1 plus C3 times 0 minus 3 2. This is 0 vector. So this is same as C1 plus C2 plus 0 into C3, that is 0, and then 2C2 plus minus 3C3 and minus C1 plus C2 plus 2C3. This is 0, and you can write it as C1 plus C2 is 0, 2C1 plus 2C2 minus 3C3 is 0, and minus C1 plus C2 plus 2C3 is 0. So this system can be written in a matrix form. What will be the matrix? It is same as A times this matrix, A times C1, C2, C3 equal to 0 matrix. Okay. What is A? A is the coefficient, that is 1, 1, 0, 0, 2, minus 3, minus 1, 1, 2. Now, when this system has unique solution, that is when this system has only trivial solution.
If determinant of A is non-zero, that is A is a non-singular matrix.
Yes. So we need to check determinant is non-zero. Okay. So let us see determinant of A. This is same as 1 times 4 plus 3, 7, minus 1 times minus 6, and another thing is 0. So it is 13, which is non-zero. Therefore, this system star has unique solution, which is C1, C2, C3, everything's at 0. Is it clear? So we have started with a linear combination, and if this linear combination is a 0 vector, we conclude that those individual scalar are 0. What does this mean? This means the vectors v1, v2, v3 are linearly independent. Okay, in short, I am denoting by Li, linearly independent. Is it clear?
Yes, sir.
Now we need to check that not only linearly independent, this also span the whole vector space. Span of these three things will give the whole vector space. That is, in geometry, you can thought as there are three straight lines: x-axis, y-axis, z-axis. These three straight lines span the whole thing. Not only these three straight lines, instead of taking any three straight line which are not, that is, third straight line must not belongs to the plane of other two straight line, then we can conclude that this span the whole space. Okay, this is what this says. Yes, in R3, three linearly independent vectors span the whole space. So what he have said is right, because instead of checking if it is spanning the whole space or not, we can directly conclude, because R3 has dimension 3 and any three linearly independent sets, linearly independent vectors span the whole space. It is true. So you can use that, or otherwise you have to prove. You have to take n vector x1, x2, x3, and you have to show that it can be written as some scalar times alpha 1, okay, and some scalar plus some scalar times alpha 2, some scalar times alpha 3. There are many questions. Let us stop here. So, is there any question up to this? Okay. What is your question, Ravi? Sir, how to proceed with proof? Okay, the proof. Let us proceed. So, span. We need to check about if it is spanning or not. So let x1, x2, x3 be any vector in R3. Now, can we write x1, x2, x3 as linear combination of those three vectors? That is, can you write x1 as c1 alpha 1 plus c2 alpha 2 plus c3 alpha 3? We have already checked that this is same as this. So, can you write this? So, first we'll assume let C1, C2, C3 belongs to some real. If this system has a solution, then the answer is yes. We can write in terms of the solution. So, will there be any solution? Is there exist C1, C2, C3 such that you can write anything as this combination? Anything as this combination? Can you write this? That is, this is same as saying C1 plus C2 equal to x1, 2C2 minus 3C3 equal to x2, and minus C1 plus C2 plus 2C3 equal to x3. This has a solution. As earlier we have seen that determinant of the matrix is non-zero. Therefore, this system, so let us denote it by double star, determinant of the same matrix, that is 1, 1, 0, the coefficient matrix, 0, 2, minus 3, minus 1, 1, 2. Therefore, double star has a solution. It will be inverse of that matrix times x1, x2, x3. Okay. That is, let us write the explicit solution. You can write C1, C2, C3 as inverse of this matrix. If we denote it by A, it will be A inverse times X. Now you have to figure out what will be the inverse and just multiply. Then you can, there will be C1 is some combination of x1, x2, x3 and same as C2, C3. Is it clear? Okay, great. Let us stop here. If any
Sir, my question is regarding basis. We take basis of zero vector space is empty.
yes,
How, sir?
it is actually convention.
Why?
You can say it is a logical convention.
Can you give logic behind this? Because I didn't find any idea why we take empty
Okay,
set
let us
as a
let us
basis for
prepare
zero
paper
vector
for this.
space.
So, what will be the basis for Rn?
Basically, it is E1, E2, E3 like this.
E1, E2,
E3 up to En.
En. So you can say R2 has basis of E1, E2, and R1 has E1 basis. But now, what will be basis for R0? R0 consists only 0. That is, instead of 3 space, you are seeing the plane only. Instead of plane, you are seeing a straight line. Instead of straight line, now you are seeing the only point, origin. What will be the thing which span the origin? 0 cannot span the origin.
Yes,
So
sir, because
there is
zero.
nothing. Yes. So it is spanned by nothing. So that's why we are saying 0 is span of nothing. Sorry, you can write. Now, is it making a sense? I
A
hope
little bit, sir, not
yes.
completely.
Not completely, but you need to work with some example, then it will be more clear. Okay, Ravi, I am saying that for R0, you cannot choose anything because 0 itself linearly dependent. So you cannot put anything here. Okay, it is a logical argument. Okay, so let us stop here. If you have any doubt. Okay, okay. Thank you, everyone.
Thank you.
Thank you, sir.
Sir, here we get the links.
I have shared link for the YouTube video and for these notes also. You can access it in that portal, that is in NPTL.
In YouTube, no, sir.
It will be NPTL. It will be in the NPTL. Okay. Or let us give you the explicit reference. Okay, let us. So, can I share it? I'm sharing it in message. This is, and this is YouTube link. Okay, then let us stop. Thank you.